Hello everyone and welcome to another Leetcode. So today we'll be doing a Leetcode easy question, which is on trees again, and that's to find the lowest common ancestor of a binary search tree. So an ancestor simply means that given two nodes, we can find something at the top that will eventually help us trace down to the nodes respectively. However, based on the definition of the lowest common ancestor on the Wikipedia, it's also possible that the two nodes that we're looking at can just be maybe something like this. So a node can also be a descendant of itself. So let's just take a look at two examples to help us understand this question. So for example 1, we see that the values given is 2 and 8, which are this node and this node respectively. And as such, the thing above both of them that connects the two of them is the 6 right here, which is coincidentally the root. So as such, we'll return the value 6, as seen in example 1. And for example 2, we are given the values of 2 and 4 respectively. So the output right here is going to be 2, because like what we mentioned, a node can be a descendant of itself. So that means for these 2 and 4 right here, it's possible for this 2 to be the one that is the common ancestor. And as such, we return the value of 2. Now we have to further take a look at the constraints that the question gives, which is that, and the most important things that we have to take note is that the P and Q will always exist in the BST. So this means that we don't have to check for the value not being there. And another thing that we have to take note is that the question conveniently gives us P and Q as P less than Q, but that might not always be the case, so we have to check for the greater one. So this is something to take note, not always. Okay, as always with this kind of questions, we will use the power. The first thing that will come to my mind is to use the idea of recursion. Okay, so off the top of my head, what I would think first is that basically if there are ones who need to be a common ancestor, right? So there's A and B and C, right? What is always true is that for a binary search tree, we will have it such that B will be smaller than A and A will be smaller than C. Okay, so if we have already made such an outcome, right, we can be sure that at that point in time, this will be the smallest ancestor. Because as you can see for the examples right here, we see for 2 and 8, they are there, and as such we have 6 in the middle. But we also have to check for the condition where the lowest common ancestor is equal to the value itself, like in example 2. So when it's 2 and this is 4, if we are given 2 and 4, then we can just straight away return 2 as well. So basically the idea will be just relatively simple. So we are given P, we are given Q, and let's treat the common ancestor as maybe A. Okay, so what we can do is just simply check at the current root, we check if this condition holds. So P less than A less than Q. Okay, if this condition holds in the first place, then that will mean that A is the lowest common ancestor. However, if you are given a case whereby this invariant does not hold, it's an invariant by the way, then we have to consider the further cases. This should instead be P less than or equal to A and less than or equal to Q. Because like what I mentioned, we should check for the condition whereby it can be equal. Okay, and then after that, we take a look at what happens if this condition doesn't hold. So let's say we are given a scenario whereby A is larger than Q. So if that's the case, right, then that will mean that it will instead be something like this. Then it will be something like this right here, right? Because for the binary search tree, the left subtree will always be smaller than the right subtree. So this means that my Q needs to belong somewhere to the left. So if that's the case that happens, right, then what we will do is to just simply recurse left and then check this new node right here to see if it follows this invariant. So if indeed does follow, right, then that will mean that it's correct. Or alternatively, we have to take a look at another case, which is when A is actually lesser than P. So that will mean that P is in fact greater than A, and so the diagram will look something like this. Right? Because we know that everything to the right of A will be larger than it. So when this happens, instead of recursing left, what we have to do is to recurse right and then check the value here to see if this condition holds. Okay, so this will be how our general algorithm will run, but we always keep checking down the correct pathway that will lead to us finding the lowest common ancestor. And we don't have to account for the fact that you might have null conditions because we know that P and Q will always exist in the BST. So that will be how the algorithm will flow, and I'll just move on to the coding explanation now. Okay, so as always, let's start with some pseudocode now. So we simply check current value if it's greater than P and greater or equal greater or equal to P and less than or equal to Q. If so, we have found the LCA. Else, we have to check if my current value is greater than Q. So that will mean that I'm actually too far to the right, so I have to go and visit the left side of the subtree. So I recurse left. Else that will mean that I should actually need to recurse right, because the LCA will lie on the right side. Because right now the current root I'm looking at is too small. Okay, so right now we can just write out the code. So take note that as I said previously, P may not always be less than Q. So you have to always check which one is the bigger one of them when we look at this comparison. So just simply say if the minimum or the P's value and Q's value is less than or equal to my root's value and less than or equal to the maximum of it, then what we'll do is just simply return the root because we have found the ancestor. Else we check my root value is greater than my Q value, then I need to recurse to the left. Root dot left and PQ. Else that will mean that I am too, okay, I forgot the if statement right here. Else that will mean the other case will be I have to recurse to the right. Lowest common ancestor, root right, P and Q. Okay, so maybe for example, let me just run through with example 2 so you can see how this code flows like. So let's say we are currently at 6 and we want 2 and 4. So you see that 4 is less than 6. So my if here will execute to recurse to the left. So we'll now be at 2. And when it's at 2, then this one will execute. Because right now this condition will hold. Then as such, I'll return the root. So basically, I'll be returning 2. Okay, this should be root dot. Yeah, then I'll be returning the root. So yeah, I guess this is how the algorithm go, and I believe it should work. So for the time complexity, I believe that it should be of O of n. Where n is the size of the tree, because we have to look through everything. And it's not given that the binary tree is balanced, so that's why we're looking at it as a O(n). And for the space complexity, if you consider it as a recursive stack, it will be O of n as well. But if you don't consider the recursive stack, then we can just take it as O of 1, which is constant. So yeah, I guess this solution should work. Solution does work, although it's actually not very fast apparently. And yeah, if you have any questions, then feel free to leave them in the comments down below. And if not, thanks for watching, and yeah, I'll see you.